Anand has already talked to you about recommender systems. And so far, we have learned how to do collaborative filtering recommender systems and how to do profile-based recommender systems. What we will do today in this lecture, we will look into latent factor recommender models. So basically, the idea will be that we will adopt this machine learning perspective where we'll be using optimization in order to build very accurate recommender systems. And in particular, our lecture today will be motivated by the Netflix prize, right? So Netflix is a company that is renting out DVDs. And in order to increase customer experience, Netflix wants to be able to recommend which customers will like which movies. And this is called the movie recommender system, right? And a few years ago, actually, Netflix prepared some data and created a grand challenge where the idea was who can build the best recommender system, and the person that does that gets $1 million prize. So here is how the competition was structured. So the idea was that first scientists would get training data. This is a set of data of 100 million ratings from 480,000 users and around 17,000 movies. And this is 6 years worth of data from 2000 to 2005, right? So based on this data, the idea is that we build or create a recommender system, and then we would send these recommendations to Netflix that would check our predicted recommendations, basically how much does a given user like the movie, with their test data set, which is a set of ratings that only Netflix has. And this way, we would want to predict and make sure that the predicted ratings correspond to the actual true ratings of the people who like those movies. So that's basically the idea. So we are given 100 million movie ratings, and we want to build a recommender system out of this. So the way we can think of our ratings data is in terms of the utility matrix R. And basically, the way this matrix is composed is that rows correspond to movies and columns correspond to users. And this matrix, most of it is empty in a sense that most users haven't seen most of the movies, right? But whenever a user sees a movie and rates that movie, that represents an entry in this matrix, right? So for example, this entry in this particular element of the matrix, number 5, that would mean that a user in the fourth column liked the third movie a lot and rated it given 5 stars, right? So now, given such a matrix, we want to formulate the recommendation problem. The way we think of the recommendation problem is in a sense that we want to predict how much will a given user like some movie that they will see in the future. So in this sense, we can use the historical rating data to build our model. This is what we will call the training data. And then using this trained model, we want to predict how much will users like movies that they haven't yet seen. And we will call this the test data. And now when I say that we want to predict how much will a user like a given movie, the way we want to quantify how accurate is our prediction, we will use what is called the root mean squared error. So basically, the idea will be that our goal is to make predictions about how much users are going to like the movies. Then we will go and ask these users, hey, how much do you really like that movie? And then we want the prediction and the true value to be as close as possible. So the root mean square error, the way the formula works, is as follows, right? For a given user X and movie I want to predict how much will that user movie pair, what will be the rating of the user X to movie I. Of course, I also know the true rating for movie I of user X. And what we want to do is we want the discrepancy between the predicted rating and the true rating to be small, in a sense that we want to take the difference, square this difference. The reason we want to square is because the difference can be either positive or negative. So if we square it up, everything is positive. Now we sum all these errors across all the users and all the movies. We take the square root and divide by the total number of ratings, and this is called root mean square error. So in some sense, our goal is to, in some sense, complete this matrix R wherever the values for ratings are unknown, and our goal is to complete this matrix as accurately as possible. So in some sense, we want to predict how much is a given user going to like a given movie. So what is the input and what is the output? right? So what Netflix gives us is the training data of 100 million ratings, so 500,000 people, 20,000 movies, and the ratings. Our goal is to predict a few ratings for every user, where the evaluation criterion, or the way how we evaluate how good are our predictions, are based on the root mean squared error. And what we also know, for example, is that the root mean square error of the Netflix system that was used in-house at that point in time was 0.95. Okay, so in some sense, on average, this in-house recommender system was about 1 star away from the true rating, right? So this competition that was taking place in 2009 and 2010, more than 2,700 teams joined the competition. And what Netflix also said was, whoever is able to improve their in-house recommender system by 10% gets $1 million prize, right? So the idea is, how can we beat the in-house recommender system and get the root mean square error from 0.9 to 0.85? That's the whole idea. Now, the structure of how to do this is the following. Basically, a modern recommender system today is composed of several different components. And the idea is that basically we want to adopt this kind of multi-scale modeling approach to the rating data. And the idea is that we want to combine several different views of the data, from this kind of global top-level view of the data to some kind of regional modeling of the data, all the way down to very local interactions between movies and the users, right? And what the goal of today's lecture will be, that we basically focus on the regional, or the middle-level modeling of the data through matrix factorization. So the methodology that we'll be using to achieve our modeling will be through matrix factorization, which relates very nicely to the singular value decomposition and dimensionality reduction lecture that we talked about previously. But before we kind of go to the main body of today's lecture, let me talk to you about global modeling and also about collaborative filtering, which is a local way of modeling the data. So what do I mean by global modeling of the data? The global modeling of the data is basically that we want to kind of compute some average rating over the movies and also over the users, right? So if we would use a global way to model how much will a given user like a given movie, then we could say the mean movie rating in our data set on Netflix is 3.7 stars. And then we could say, oh, but for example, the Sixth Sense movie is rated half a star above the average rating. And then we could say, oh, but this given user is very critical. So they tend to rate things about 2.2 stars below the average rating, right? So we could now say, okay, so 3.7 is our baseline. Now we have a movie that is above average for half a star, so that is 4.2. But this person, Joe, is a critical person, so they tend to be 0.2 stars below the average. So 4.2 minus 0.2 equals 4, right? So in some sense, our prediction, how much will Joe like the Sixth Sense, would be 4 stars. As I said, because of 3.7 plus 0.5 minus 0.2 equals 4.0, right? So this is how basically, just based on the average of the user rating and average of the movie rating and overall average rating throughout the data set, we can already make a prediction how much will a user like a given movie. Of course, this is a very crude, very global prediction, but it turns out to be very useful. So this is at the end, one end of the spectrum. On the other end of the spectrum, we can use very kind of local neighborhood properties of a given user and a given movie to make recommendations. And this is what collaborative filtering does, right? So in some sense, the idea would be the following, right? So I would like to estimate what are other movies that are similar to the Sixth Sense that Joe also rated, and based on this, I would then make a recommendation, right? And based on these kinds of signals, I would then make a final estimate that Joe is going to like our movie or rate it with 3.8 stars. Okay? So how does collaborative filtering do what I just said? The idea is basically the following, is that we want to derive unknown ratings from the ratings of similar movies, right? This is the item-based collaborative filtering. So now the big question with collaborative filtering is, how do we operationalize the notion of similar, right? So I basically need to define a similarity measure that tells me how similar are movies I and J. And now that for every pair of movies, for example, I'm able to measure the similarity, then the idea is the following. Given that I want to make a recommendation for movie I, the way I would do this is I would go find k nearest neighbors, basically k most similar movies to movie I, and then I would ask the ratings and add them together in a weighted combination, where movies that are more similar to my movie I, they have a higher weight. So this is the formula that I have at the bottom, so let me explain it, right? So what we want to do is we want to predict how much will user X like movie I. The way we do this is that for a given movie, and we go and find, let's say, k nearest neighbors, meaning k most similar movies J to this query movie I, and then we say, what was the rating that this user X gave to that given movie I? And then we also multiply this with the similarity between movie I and J, right? So the idea basically is that if movies I and J are very similar, then Sij will be high. So the rating that user X gave to movie J will have a high weight. If the movie J is of low similarity with I, then what will happen is that that rating of user X to the movie J will have a low weight in this summation. And then at the bottom, we just normalize, right? And this is one way how we can compute the rating based on the collaborative filtering. Now, how do we put together the local effects and the global effects, right? How do we combine collaborative filtering with the global effects model that I described 2 slides ago? The way we do this is that basically we just add the two together, right? So here's the formula that I will explain again, right? So my recommendation or prediction of how much will user X like movie I is the baseline predictor, which is what we talked before, right? So the baseline predictor for user X and movie I is simply the average movie rating plus the average deviation for user X plus the average deviation for movie I, right? So in our previous case, B of X was minus 0.2 because our user Joe was very critical. And in our case, The Sixth Sense was a good movie, so the bias of that movie was 0.5. And the overall rating was 3.7, right? So our baseline recommendation for Joe at that point in time was 4.0. And now, of course, this is our baseline recommendation. And now we can take the part from the collaborative filtering, where we take k closest movies J to the given movie I, and ask what is the deviation of the user's rating with regard to their baseline for that movie, and take a weighted combination of this and compute the recommendation, right? So here the first part is the global part of the model, and the second part is the collaborative filtering part of the model. Of course, here are a few caveats, a few things to be careful about. First one is that coming up with the good similarity measure, basically the good Sij, is very hard. In some sense, it's arbitrary, or one has to try many different metrics before one starts to work. The problem with pairwise similarities is that basically they consider the similarities between the movies, but they kind of ignore the similarities between the users. And another thing here we could say is that taking this weighted average sometimes can be restricted. But these are kind of, if there are some issues with this model, these are the three to talk about. But in practice, this already works quite well. So let me show you how well do these different models work. Okay? So what I'm showing you with this yellow arrow is what is the performance of various methods on this Netflix prize, right? For example, if for a given user we would just go and predict the global average, so we would just compute what is the global average star rating on the whole Netflix data set, and whenever a user comes, we would just say 3.7. That's our prediction. If we do that, our root mean square error would be 1.12. Right? So if we are kind of very naive and don't even look at the user, just always give the same recommendation, our root mean square error would be 1.12. if, for example, for every user, we would say, we don't even care what is the movie this user is going to watch. We will just go and predict the average rating for that movie. That already decreases the error, right? So if for every user we just predict what's their average rating, that reduces the error to 1.06. Now, for example, I told you before that the Netflix recommender system was at 0.95, right? So kind of much better than these naive global models. But for example, the simple collaborative filtering that I told you before already beats the Netflix model. So the collaborative filtering that we just talked about gives you the score of 0.94, which is, 1 percentage point better than the Netflix model. Of course, the $1 million model is down here. We need to be at 0.85. And what we will do now in the rest of the videos on recommender systems, we will learn how to basically go all the way down to here and how kind of win $1 million. So right now, collaborative filtering is at 0.94. The question is, what kind of methods can we use to get all the way down and reduce our error to 0.85? So that's the idea.